Hello students, welcome to the lecture 4 of design of bridges. So today we are going to see about the design of solid slab bridges. So in this we are going to see about let's start up with the types of culverts. So the culverts, as we know, the culverts are the small bridges which are mainly constructed when the span is less than 6 meter. So the culverts are constructed with various materials and the different designs. The popular forms of culverts are the temporary stone scuppers, stone slab culvert with abutment and piers, RCC slab culverts with abutment and piers, RCC box culvert, RCC pipe culvert, metal pipe culverts, and the masonry arch culverts. So in this lecture we are going to see about the different types of culverts, and also we are going to see a design on the stone slab culvert design. So first of all, what do you mean by a temporary stone scuppers? So now let us discuss the temporary stone scuppers. The scuppers are simple drainage opening provided in the bridge decks or abutments to allow rainwater on the surface water to flow out. So preventing waterlogging on the deck surface. So it's a temporary or the low cost constructions. Instead of using the RCC or the steel pipes, the small openings are left in the stone masonry itself. So these are called as the temporary stone scuppers. So they're usually formed by leaving gaps between the stones or the walls. If you see, the size of each scuppers is small, about 100 to 150 millimeter. So the main purpose is to carry away the surface runoff water. While they are simple and economical, they are not very much durable. So they clog easily and with the silt and the debris and cannot handle large discharges. So hence they are mostly used in the temporary bridges, culverts, or rural roads, and are laterally replaced with the RCC pipe scuppers if it is used for the permanent structures. So the next one is now let us discuss about the uh, slab culvert with abutments and piers. So this type of culvert is one of the oldest and the simplest form of bridge construction, commonly used in the rural and the temporary works. So in this we see the large stone slabs are placed across the span to form a deck or the roadways. So these slabs are supported at the ends by the abutments, and for the longer span, intermediate piers are provided to divide the span into smaller sections. So the abutments act as a main load-bearing walls at the ends of the culvert, transferring the loads of the stone slab and the traffic to the foundations. When the plan exceeds the length, then a single stones can cover the piers or constructed between the abutments. So these piers serve as an intermediate supports, reducing the effective span of the slab and allowing the more stability. So the stone slab culverts are simple, low cost, and durable under moderate traffic. However, they are suitable only for the small spans, generally for 2 to 3 meters, because of the limitations in size and the strength of the slab. So they are often found in the old village roads and the minor irrigation works. So this stone slab culvert can be constructed for the rural roads and the other district and the village roads. So next we see about the RCC slab culvert. So these are the modern and the widely used type of the culverts constructed with the reinforced cement concrete. So in this form of culvert, a reinforced concrete slab is placed across the span, supported on the abutments of the walls. So the reinforcement in the slab resists the bending and the shear force caused by the vehicular load, while the concrete provides the durability and the compressive strength. Compared to the stone slab culvert, the RCC slab culvert have several advantages. So they can be used in the design. They can be designed for the larger span, usually up to 8 meters. depending upon the traffic load conditions. They are strong, durable, and capable of carrying heavy loads such as highway traffic, including IRC Class AA loading. The RCC design also allows for the flexibility in the design, ensuring proper drainage, durability, and safety as per the IRC codes. So the RCC slab culverts are easy to construct with locally available materials like cement, sand, aggregate, and steel. So they also require less maintenance compared to that of stone slab culvert, and provided with a smooth riding surface for the vehicles. Because of their strength and serviceability, they have largely replaced traditional stone slab culvert with this culvert in the modern construction. So this RCC slab culvert with masonry abutments and piers can be constructed for the individual span up to 6 meters. So next one is RCC box culvert. So the RCC box culvert are ideal for in situ constructions for opening of up to 5 meter. So they can be constructed in the square boxes or rectangular boxes depending upon the site conditions. Single or the multiple boxes can be constructed. The advantages lies in the elimination of stout abutment sections which are unavoidable in the slab construction. So this box culvert replaces the use of abutments like in case of a slab culvert. So unlike slab culvert, which consists of a simple RCC slab resting on an abutment, the box culvert are constructed in the form of a rigid reinforced concrete boxes. So this box has a top slab, bottom slab, and a side walls, all cast monolithically to act as a single structural unit. So the RCC box culverts are particularly suitable for situations where the discharge is moderate to high and where the height of the embankment is limited. So they are commonly used under the roads and railway embankments to allow cross drainage of the water streams, stormwater, or even pedestrian passage. So one of the main disadvantages of the box culvert is they are structurally so the main advantages of the box culvert is that they are structurally efficient, since the top slab and the bottom slab shares the bending moment. So the required thickness of the slab is the required thickness of the box culvert becomes the minimum, making them economical. So they have a better hydraulic efficiency compared to that of a slab culvert, because the full cross-sectional area is available for the water flow. So these are the advantages of we have seen the advantages of RCC box culvert. So next we'll see about the pipe culvert. So the RCC pipe culvert, these are one of the most common and the economical form of the culvert used for the small and the medium discharges. So in this type, the reinforced concrete pipes are placed side by side under the road embankment, allowing for the water to flow through. So the pipes are designed to carry both the earth pressure from the embankment and the live load from the vehicle above. So the pipe culverts are generally circular in sections and are manufactured as a precast RCC pipes, which make them quick and easy to install. So the number of pipes provided depends upon the required discharge capacity. For longer discharge, multiple pipes are laid parallel to each other. The ends of the culverts are finished with stone masonry or concrete head walls to support the pipes and prevent erosion. So the RCC pipe culverts are most suitable where the natural ground level is low and the depth of the earth cover above the culvert is not very large. They are hydraulically efficient for smaller span and carry heavy highway loads when properly designed as per IRC specifications. The common diameter of the RCC pipes used in culverts ranges from 0.6 meters to 1.8 meter. So So these reinforced concrete pipe culverts are ideal for dealing with small discharges. The advantages are they're very economical. So in the circular sections is most ideal for withstanding forces from all around. Since the pipe do not need very elaborate bedding, the cost further comes down. So the pipe culvert do not demand structural design for individual cases. The pipes are standardized in terms of mix, thickness and reinforcement. The pipe can be cast strictly controlled conditions at a central plant and thus requires quality assurance. The quality is assured. The disadvantages with the pipe or they cannot be used for the large opening. The minimum cover of at least half the diameter of the pipe is to be ensured over the pipes. So this is the granular bedding required for the pipe culvert. So the granular bedding, which consists of forming and grading the bedding with sand or the granular material passing 4.75 mm is normally provided. The thickness of the bedding layer should be minimum 75 mm. So such bedding is suitable for fills up to 4 meter height. So the concrete cradle bedding, which consists of M15 grade of concrete. So thickness of the bedding should be minimum 250 mm. So such bedding is mainly used for the height of fill about 4 meters, above 4 meters. Next one is the masonry arch culvert. So this is one of the oldest form of culvert which is widely used before the development of reinforced concrete. So in this type, the superstructure is built in the form of an arch including the stone masonry or the brick masonry. The arch transfers the load mainly through the compression, which makes it very effective since the stone and the brick have the high compressive strength. The abutment and the wing walls provide support to the arch and transfer the load safely to the foundation. The curved shape of the arch helps in spreading the loads towards the support, reducing the bending stresses. So this makes the masonry arch culvert durable and strong from small to medium span, usually up to 6 meters. So this type of culverts are very economical and where the stones or brick is locally available. So they are also aesthetically pleasing and blends well with the surrounding environment, which is why they are still found in the old roadways, railways and heritage structures. So this is a slide showing the type of bridges and their suitability. So if you see the masonry arch, it requires a good foundation for the span of up to 15 meter. The RCC simply supported slabs are suitable for any type of foundation span. You can provide any type of foundation for spans up to 10 meter. The RCC T-beam and the simply supported slab, it also it is suitable for any type of foundations and spans large from 10 to 25 meters. Next, continuous T-beam and the slab bridge. It's mainly provided for the rocky and yielding foundations for span up to 10 to 20 meters. RCC balanced cantilever, which requires a deep foundation and spans ranges from 25 to 60 meter. The precessed tree beam and the simply supported slabs. You can provide any type of foundation, generally deep, for the spans ranges from 20 to 60 meters. Next one is a pre-stressed segmental balanced cantilever, where the deep foundation, it requires a deep foundation and the spans ranges from 60 to 100 meter. And then the cable stayed bridge, which requires a deep foundation and the spans ranges from 80 to 500 meter. So this is a picture of an RCC slab culvert. Here we can see it's at the deck slab, and then you have the abutments or the wing walls. So here you can see the deck slab, the curbs and the wing walls and the abutments and the so this is a picture showing the component part of a slab culvert. So this wing walls are mainly provided to retain the soils, and this abutment acts as a support which helps in transferring the load from the deck slab to the foundation. So let's see about the design of a reinforced concrete slab for the IRC Class A loading. So, so we are going to design an RCC concrete slab culvert for a national highway to suit the following data. The carriageway width is 7.5 meter wide. It's a 2-lane. The footpath on the either side is 1 meter wide. The clear span is 6 meter and the bearing court is 20 meter. The width of the bearing is 400 mm. The grade of concrete and the steel used are M25 and Fe415 grade HYST bars. The loading, the bridge is the slab culvert is designed for the IRC Class AA tracked vehicle loading. So the codes we are going to use are IRC 6 and IRC 21. So they design the reinforced concrete slab deck and sketch the reinforcement details in the longitudinal and the cross section of the slab. So we'll see the design. So this picture shows the cross section of the deck slab. So here the cross section of the slab, the carriageway width is 7.5 meter and the footpath, and we have 1 meter footpath on the either side of the carriageway. The next we have this the effective span of the slab is the span of the deck slab is 6 meter, which is in this longitudinal direction. So the effective span is equal to the clear span plus effective depth, or the clear center to center of the bearing. Since we know the bearing length is the width of the bearing is 400 mm on the either side. So it is the clear span 6 meter plus the overall thickness of the slab is assumed to be 500 mm. So the effective depth is considered to be 460 mm. So the effective span is equal to clear span plus effective depth. So it is 6 plus 0.46, that is 460 mm, which is 6.4 mm. And similarly, the center to center of the bearings, it is 6 plus 0.2 plus 200 mm plus 200 mm on the either side. So it is 6.4 meter. So therefore the effective span L is equal to 6.4 meter. So this is the cross section of the deck slab. So we have a bearing court of 80 mm, which is already given in the problem, and the 1000 mm and the 1000 mm is the footpath on the either side of the deck slab. So the overall length of the deck slab is 9.5 meter and the span is minimum of about 2 values. So it is taken as, the effective span is taken as 6.4 meter. So the next step of the design of the culvert is the calculation of the loads. So the loads includes the calculation of the dead load and then the live load. So the dead load is the sum of the sulfate of the slab. So sulfate of the slab includes the dead weight of the slab plus dead weight of the bearing post. As we know, the thickness of the slab is equal to thickness of the slab is 500 mm. So the dead weight of the dead load of the slab is thickness of the slab into unit weight of concrete, which is 24 kilonewton per meter cube. So the total load is 121 newton per meter square. Next one is the dead load of the bearing core. So it is 80 mm thick bearing core. So it is 0.08 into 22 is the unit weight of the bearing core. So it is 1.76 kilonewton per meter square. So the total load is therefore the total load is, sorry, I have mentioned it as 121, but it is 12 kilonewton per meter square. Therefore the total load is 12 plus 1.76, so it is 14 kilonewton per meter square. So as we know, the bending moment, since it is a simply supported slab, the bending moment is WL square by 8. So the total load is 14. So the total load is 14 multiplied by the effective span is 6.4. So it is 14 into 6.4 the whole square divided by 8. So it is 72 kilonewton per 72 kilonewton meter. So it is the dead load bending moment. So the next step is to calculate the live load bending moment. So as we know, for IRC Class A tracked vehicle, the impact factor for the IRC tracked A vehicle is 25% for, it is 25% for 5 meter, and it is decreasing for 10, and it is 10% for 9 meter. So we have to calculate what is the impact factor for a span of 6.4 meter. So you have to do the interpolation and find out the impact factor, which was found as 19.7 percentage. So the next step is to calculate the live load bending moment. As the live load bending moment is nothing but the vehicle load which will be coming on the slab. So since it is a class CE vehicle, so loading pattern and the nature of vehicle coming on the slab has to be examined, and the live load has to be calculated. So coming to the next one is the wheel load on the slab. A wheel load is practically considered as a concentrated load on the slab. This load will get dispersed with its effect along the span wise and the width-wise direction. So the wheel load is considered to be a point load which is acting on the slab, since the wheel has some contact area. So this wheel load will have some load dispersion along the lengthwise and the breadthwise, which has to be calculated as per the codal provisions. So this wheel load can be calculated by using three methods. One is the effective width method, another one is Gauss coefficient method, another one is the Westergaard's method. The first method is applicable only for the one-way slab which is supported on the two opposite side edges. The second method is used for the two-way slabs which are supported on the four edges, whereas the third method is seen to be a complicated one, and therefore it is rarely adopted for the slab design. So next see about this effective width method, which is commonly adopted in this calculation of effective width and breadth of the live load. So as mentioned earlier, this method is applicable only when there is a one-way action prevail for this slab. The slab needs to be supported only on two edges. In our case, since it's a slab culvert, we have the two supports. So however, for very long spans may be supported on all four edges. So this method is based on the observation that it is not only the strip of the slab immediate below the load that participates in the action, but also a certain width of the slab also take part into this effective with the load dispersion. So the width of the slab over which the action of the load prevail is known as the effective width of the dispersion. The extent of the effective width depends upon the location of the wheel load and with reference to the support and the dimensions of the slab. So thus the concentrated load virtually transformed into a uniformly distributed load. So we consider this wheel load as a point load which will be transformed into a uniformly distributed load based on the size of the wheel. So it is distributed along the sum length, that is the dispersed length along the span, and the width, which is called as the effective width. So this is shown in the figure. The IRC 21 recommends formula for computing the effective width of the slab for the two types of slab. One is the simply supported slab and the cantilever slab. So which we'll see. So if you see this, so this figure shows the load dispersion pattern on the slab. So here you have this wheel, the wheel imprint, in which this is the vehicular movement. This is the span of the center to center distance between the support, and this is the vehicular movement. And if you see this, the length of the wheel along the span is the effective length, and the perpendicular direction and the transverse direction we have this effective width. So the wheel imprint, that is the effective length of load dispersion, is calculated by using the formula which is prescribed in the IRC code 21. So the bending moment per unit width of the slab is caused by the concentrated load on the solid slab spanning in one direction. or on the cantilever slab may be calculated using the width of the slab that may be taken as the effective in the rest of the bending, in resisting the bending moment due to the concentrated load. For precast slab, the term actual width of the slab used in this class shall indicate the actual width of each individual precast units. So for the solid slab in one direction, for the single concentrated load, the effective width may be calculated in accordance with the formula. B effective is equal to alpha is into 1 plus 1 minus A divided by L0 plus B1, where B effective is the effective width of the slab on which the load act, and L0 is equal to the effective span as indicated in the class, and A is the distance of the center of gravity of the concentrated load from the nearest support, and BL is the breadth of the concentration area, the dimension of the tire or the track contact over the load surface of the slab in right angle with the slab plus twice the thickness of the bearing coat or the surface finish above the structural slab. So substituting all these values, we can calculate the effective width of the slab in the transverse direction. So here is again the general representation of the effective width calculations. So the B effective is equal to alpha into x into 1 minus x by L plus width of B1. So x is the center of gravity of the concentrated load from the nearest sub, and alpha is a constant which depends upon the value of B by L value that we'll see in the later, when B1 is the width of the dispersion area of the wheel load on the slab through the bearing cord, which is given by W plus 2 into H, where H is the thickness of the bearing cord and W is the contact width of the wheel on the slab as per the direction of the transverse movement. So since we have the class AA vehicle, so this is the total load coming on the slab is due to the tracked vehicle is 700 kilonewton, which is transferred which is dispersed equally to both the wheels of 350 by 350. And if we see so here you can see the loading pattern of class AA vehicles. Here you have a tracked vehicle. So the total weight of the tracked vehicle is 700 kilonewtons, and so it has the two wheels. The load is distributed equally among the two wheels. So each wheels carries a load of 350 kilonewton and 350 kilonewtons. And here you can see the contact length along the span direction is 3.6 meter. So the minimum value of clear distance to be provided is 1200 mm. For a multi-level bridge greater than 5.3 meter, the minimum clearance to be provided is 1200 mm. So in our problem, we have provided a clear spacing of minimum clear distance of 1 meter. So the next step is the calculation of the effective width of the slab. So the effective width of the slab, we have already seen the formula. B effective is equal to alpha x into 1 minus x by L plus B1. So this alpha, it is a ratio which depends upon the factor B by L, where B is the breadth of the slab and L is the length of the effective length of the slab. The breadth of the slab is given by 7.5 meter plus 1 meter carriageway on both the sides. So the total breadth of the slab is 7.5 plus 1 plus 1, so it is said to be 9.5 meter. So already we knew that the effective length of the slab is effective span of the slab is 6.4 meter. So this B by L is equal to 1.4. So if you see this, if you interpolate the value between 1.4 and 1.5, and roughly we'll get this alpha value, which is this K value, which is represented as K here. So K is equal to 2.84. So substituting the K value into X. So the X is the distance between the center of the load to the center of the load, and the load is placed in such a way that the minimum clearance is provided. So the clear spacing of 1.2 meter is provided on the left side. So this spacing is found to be 1.2 meter. Minimum clear spacing is provided. So the X is found to be so the distance X is calculated, which is 3.2 2 meter. So substituting all these values, we get this is alpha is equal to 2.84 and x is equal to 3.2. 1 minus 3.2 divided by the effective length is 6.4 meter plus the effective width of dispersion, which is given by, which is nothing but the width of the contact surface, the width of the tire plus 2 times the thickness of your plus 2 times the thickness of the wearing coat. So it is 1.01 meter, which is already given, which is already described in the code book. So the tracked vehicle is placed close to the curb with the required minimum clearance as shown as in the figure. So the effective with B effective is given by 5.56 meter. So next, the tracked vehicle is placed close to the curb with the required minimum clearance as shown as in the figure. So here you can see you have two wheels which carries a load of 850 kilonewton each. So sorry, which carries a load of 350 kilonewton. The width of the tire is 850. The spacing between the tires is 1200 mm, and the minimum clearance provided is 1.2 meter, and 1 meter is the width of the carriage. Is the width of the pedestrian walk. So next we are going to calculate the average intensity of the net effective width of dispersion. So we have calculated using the formula. So since there are two loads of tracks with the impact, so there is the total load for the tracked vehicle is 700 kilonewton multiplied by the impact factor. So the load is the load after the impact is 833 kilonewton. So the average intensity of the load is the load divided by the area of intensity. So it is 4.76 multiplied by effective width into effective breadth. So it is 23.61 kilonewton per meter square. So next, so based on this load dispersion and this effective length, so the maximum bending moment is calculated. So the maximum bending moment is found to be 130 kilonewton per kilonewton meter. So the total bending moment is the sum of the bending moment due to dead load plus bending moment due to the live load. So this maximum bending moment to the live load is calculated based on this previous calculation. The span is the load is placed with a minimum clearance of 1.2 meter from the left end, and it is a UDL. So the intensity of the load is already we have calculated, and we found out what is the maximum bending moment. So next one is the shear. The shear due to the tracked class A vehicles. For the maximum shear of the support, the loading is placed in such a way that it is placed next to the left end support. So the loading is placed in such a way that the minimum clear distance is not maintained, and the load is placed exactly over the support. So for this we have to, this is the loading pattern for the shear calculation. So next, similar to the bending moment, we will calculate the effective depth of dispersion for the shear. So here the load is placed, so the wheel is placed closer to the slab with no clear spacing, and so we have calculated the effective width of dispersion. So the effective depth of dispersion BE is found to be 5.256 meter. So the width of dispersion was calculated similar to that of previous case. So it was found to be 7303 mm. So the average intensity of the load is equal to your load after the impact divided by the area of intensity of the load, which is 4.76 effective length into 7.360 is the effective width. So it is 24.1 kilonewton per meter square. Next, the shear is calculated. VA is equal to, which was found to be the shear force, the support A is calculated. These steps already we know how to calculate the shear force. The shear force VA is calculated, which was found to be 72 kilonewton. So the dead load due to the shear is WL by 2. So it was found to be WL by the shear intensity due to the dead load, which was found to be WL by 2, which is found 45 kilonewton. So the total design shear force is the shear force due to the dead load plus shear force due to the live load plus shear force due to the dead load, which was found to be 117 kilonewton. So next one is the design of the deck slabs. The effective depth of the slab is computed. So we have already assumed the depth of the overall depth of this deck slab is found to be 500 mm. We have assumed as 500 mm. So we have calculated what is the effective depth required. Effective depth D is equal to square root of M divided by Q into B. So Q is the moment of resistance coefficient. So as these things we already learned in design of reinforced concrete elements, so we did not discuss more on this. So the bending moment we have it was found to be 185 kilonewton, so it is 185 into 10 to the power 6 divided by the moment of resistance coefficient, which is 1.1 into the B for per meter slab, it is 1000. So the depth D required, effective depth required is 410 mm. So the effective depth provided is 460 mm, which is greater than D required. So next one is the area of tension reinforcement. AST is equal to M divided by sigma ST JD. J is the lever arm constant. So it is 185 into 10 to the power 6 divided by sigma ST into 0.9 into 460, which is 2234 meter square. So next we will find out the spacing of 20 mm diameter bars is 1000 into small AST divided by capital AST, which is 140 mm. So adopt for the bending moment, the adopt 20 mm diameter bars at 150 mm center to center as the main reinforcement, and so to confirm the criteria of cracking consideration as per IRC 21. So therefore AST provided is 2242 mm square. So next, the bending moment for the distribution reinforcement is calculated. The bending moment for the distribution calculated is taken a 30% of live load bending moment plus 20% of dead load bending moment. So that total bending moment was found to be 49 kilonewton meter. So using 12 mm diameter bars, the effective depth was found to be 444 mm. So they calculate the AST, the spacing of 12 mm diameter bar, so it is found to be 184 mm. So providing 12 mm diameter bars at 150 mm center to center as a distribution reinforcement. So in order to prevent the shrinkage crackage, supplementary reinforcement of 10 mm diameter bars at 300 mm center to center are provided on the both of the top of the slab. So next one, check for the shear stress. The shear stress is checked as per the IRC 21-2000 specification. The shear stress is given by the formula. The design shear stress tau V is given by the formula V divided by BD, where V is the design shear force and B is the width of the section and B is the effective depth of the section. So as we all know how to calculate the shear stress, first we have to calculate tau V, then calculate tau C, check whether tau V is less than tau C. If tau V is less than tau C, minimum shear reinforcement is provided. If tau V is greater than tau C but less than tau C max, stirrups are provided. If tau V is greater than tau C max, we have to redesign the section. So the permissible shear stress tau C in the concrete beam without the shear is compiled the table 3.8. When the shear reinforcement is provided, the shear stress in the beam should not exceed the value of the maximum shear stress tau max. For solid slab, the permissible shear stress in concrete shall be calculated as per K into tau C, where K is the table which depends upon the factor beta. So for the percentage of tensile reinforcement 100 AS by BD, and for the different grades of concrete, the tau V permissible shear strength the concrete is calculated, and the maximum shear stress value are given, and the overall depth and the Ks depends upon the overall depth of the slab. For 300 and more mm, the K factor is found to be 1 mm. So the normal shear stress tau V is equal to V divided by BD. The shear force is 117 multiplied by the 10 to the power 3 divided by B into the effective depth, which is 460 mm. So the designed shear stress is found to be 0.254 Newton per mm square. Next one, for the calculation of tau C, AST for 100 AST by BD, and the grade of concrete is to be M25. The tau C is 0.3 Newton per mm square. So for solid slab, the permissible shear stress is K into tau C, where K is equal to 1 for slabs of 300 mm greater than thickness. The K is found to be 1, so K is equal to 1. So the permissible shear stress in the concrete is found to be 0.3 Newton per mm square. So since tau V is less than K into tau C, the shear stress is safe with the permissible limit. So the details of the reinforcement of the deck slabs are shown in the figure. So here you can see the details of the reinforcement. The main bar is provided, and you have a distribution bar of the main bar of 4 by 20 mm, and the distribution bar of 12 mm diameter bars at 150 mm center to center is the distribution reinforcement provided, and you have the main bars of 20 mm diameter at 140 mm center to center as the main reinforcement, and we have this reinforcement normally provided to take the shrinkage stresses. So thank you.